Hey everybody, Dr. A here, and in this video we're going to be exploring another example of internal torque moments. Okay, so let's look at the given information. Here we're being asked to use the method of sections, that's MOS, to determine the internal torque at point B. Point B is right here in the shaft. The shaft has a circular cross section. So at the far left support we have a fixed connection. And then we have this shaft that's kind of got a 3D view to it that's coming out of the fixed connection. Point B is 1 foot away from the fixed connection, and then the remainder length of the shaft is 2 feet. Across the length of the shaft, you've got an applied torque moment of 20 pound-inches per inch. So notice this is a uniformly distributed torque moment. It's not a single applied torque moment. It's a uniformly distributed torque moment, 20 pound-inches per inch, okay? And then at the free end, you have an applied single torque moment of 400 pound-inches, and it's going in the opposite direction of the uniformly distributed torque moment, okay? So what do? Well, again, we use method of sections. So we're going to say solution, and we're going to make a cut through point B. Okay, so when we cut through point B, which side of the cut do we use when we want to analyze that cut free body diagram? Well, we could analyze the left side or the right side. Does it matter? No, it doesn't. This is method of sections. You could use either side of that cut, okay? Now, if you want to use the left side of that cut, what must you calculate first? You must calculate the torque reaction at the fixed connection first, okay? However, if you choose on the front end to analyze a right free body diagram, so that's a free body diagram on the right side of this cut, you don't need to solve for that torque reaction at the fixed connection. You just use the free end here, okay? So let's do this. Let's use a right free body diagram so we do not need the torque reaction, okay? So we're gonna make the cut at point B, and we are going to draw the right side of that shaft, all right? Now what's gonna show up there? Well, we cut it specifically at point B. So this dimension line is gonna show up as 2 feet. Now, here's where you got to be careful. Notice that your uniformly distributed torque has units of pound-inches per inch, which means we probably should express this as 24 inches instead of 2 feet, all right? And then we're going to have our uniformly distributed torque moment show up there. And again, that's 20 pound-inches per inch. And then at the free end, we have that singular torque moment of 400 pound-inches. And so what shows up at that cut? Well, at the cut, I'll go ahead and use orange here. At the cut, we're going to have this internal torque T that we're looking for. I'll call it T sub B since it's at point B. Now, what we need is a viewpoint, okay? Remember a viewpoint, I sketch that as like a little eyeball, and we look in the direction that the eyeball is pointing. Now we can put the viewpoint back here and look into the cut, or we could put the viewpoint out in front and look at the free end of the cut. Either one is fine, right? You can establish a viewpoint looking in either direction. The point is you need to look along the length of the shaft in one of those directions, all right? So I'm just gonna say, let's draw our viewpoint back here and let's look into the cut, okay? And so what do we see? Well, we see a circular cross section, all right? And the first thing we're going to see is this TB that we're trying to find. All right, so again, if your eyeball is here and you're looking into the cut, this is kind of sort of 3D view. What's the first thing you see? You see TB, but from this eyeball's perspective, TB is going clockwise. Now behind TB, you see in a hidden line fashion with a dashed vector, 20 pound-inches per inch, okay? And then behind that, so I'm going to make that the next thing dashed as well, you've got the 400 pound-inches point torque at the free end, okay? And again, this is all based on this viewpoint, all right? So what do we do next? We say sum of the torques equals 0, and I'm going to say counterclockwise positive, and I'm going to do that based on that little viewpoint, this eyeball here. And so looking at this two-dimensional cross-section diagram, all right, I'm going to say negative 400 pound-inches. I'll tell you what, let me write this a little bit better so we can hopefully write it along one line. I'm going to say negative 400 pound-inches, and then I'm going to say plus 20 pound-inches per inch. Now remember that 20 pound-inches per inch, that's a distributed torque. That's a uniformly distributed torque, which means you need to get an equivalent point torque. So what do? Well, just like if this was a beam in statics, we say 20 pound-inches per inch multiplied by the length that it's distributed over. So we multiply that by 24 inches, okay? And then finally we say minus, already did the 400, we say finally minus TB equals 0. So it looks like I started with what's back here and then I moved forward when I wrote my equations, okay? And so what I'm solving for here is TB. So I'm going to do a little bit of rearranging, and I'm going to pull out my TI-36X Pro, and I'm going to say 20 times 24 is 480, and then minus 400 is just 80, and so I get 80 pound-inches. And it comes out positive, right? It comes out positive, which means that TB is oriented in the direction I assumed in that free body diagram. So there is my final answer. If you found this video helpful, please hit like and subscribe, and be on the lookout for other content like this. Thanks for watching.